NumPy performance profiling. Learn how to profile and optimize NumPy code. Profiling is an essential skill for any data scientist or Python programmer working with numerical computations. By the end of this tutorial, you'll understand how to identify performance bottlenecks, measure execution time, and make your NumPy code run faster and more efficiently. Why should you profile NumPy code? First, profiling helps you identify performance bottlenecks in your code. Instead of guessing which parts are slow, profiling gives you concrete data. Second, you can measure the execution time of specific operations to understand exactly how long each part takes. Third, profiling lets you track memory usage and allocation patterns, which is crucial when working with large arrays. Finally, profiling enables you to make data-driven optimization decisions rather than relying on intuition or assumptions. Let's start with the simplest method, basic timing using Python's built-in time module. Import the time and NumPy modules. Record the start time before your operation. Create a random array with 1,000,000 elements and square each element. Record the end time after the operation completes. Finally, print the execution time by subtracting the start time from the end time. This method is straightforward and works well for quick measurements, though it only gives you a single measurement without statistical reliability. For more accurate measurements, use the timeit module. This is Python's standard tool for benchmarking small code snippets. Import timeit and NumPy. Define your setup code, which runs once before timing begins. In this case, import NumPy and create the array. Define the statement you want to time, such as r raised to the power of 2. Run timeit.timeit with your statement, setup code, and the number of repetitions. Here, number equals 100 means the operation runs 100 times. Divide the total time by 100 to get the average time per execution. This method is much more reliable than basic timing because it runs the code multiple times and accounts for system variations. When you need to see exactly which lines of code are taking the most time, use line_profiler. First, install it using pip install line_profiler. Import line_profiler from the line_profiler package. Decorate your function with the @profile decorator. Define a function that performs multiple NumPy operations, such as calculating the mean and standard deviation. Line profiler will show you the execution time for each individual line within the function, making it easy to spot which specific operations are slow. This is incredibly useful for optimizing complex functions with multiple NumPy operations. cProfile is Python's built-in profiler for function-level analysis. Import the cProfile module and NumPy. Define a function that contains the code you want to profile. In this example, process_data creates a random array with 1,000,000 elements, sorts it, and returns the result. Run cProfile.run with your function call as a string. cProfile will show you how much time is spent in each function call, including NumPy's internal functions. This helps you understand the overall performance characteristics of your code and identify which functions are consuming the most time. Memory usage is just as important as execution time, especially when working with large datasets. Install memory_profiler using pip install memory_profiler. Import the profile decorator from memory_profiler. Decorate your function with the @profile decorator. Define a function that allocates memory, such as creating two large arrays using np.0s and np.1s. Memory profiler will show you how much memory each line allocates, helping you identify memory-intensive operations. This is essential for optimizing memory usage and preventing out-of-memory errors when working with large NumPy arrays. Here are some NumPy-specific profiling tips to keep in mind. First, always profile vectorized operations versus loop-based operations. Vectorized code is almost always faster, but profiling confirms this and shows you exactly how much faster. Second, compare different NumPy functions for the same task. For example, np.sum might be faster than np.add.reduce in some cases. Third, measure the impact of using array views versus copies. Views are faster and use less memory, but copies are sometimes necessary. Finally, test performance with different data types. Using float32 instead of float64 can reduce memory usage and sometimes improve speed, depending on your hardware. Once you've profiled your code and identified bottlenecks, here are common optimization strategies to apply. First, always use vectorized operations instead of loops. NumPy's vectorized operations are implemented in C and are much faster than Python loops. Second, leverage broadcasting for efficient computation. Broadcasting allows NumPy to perform operations on arrays of different shapes without creating unnecessary copies. Third, pre-allocate arrays whenever possible to avoid repeated memory allocations, which are expensive. Finally, choose appropriate data types for memory efficiency. Using smaller data types like int16 or float32 can significantly reduce memory usage when you don't need the full precision of larger types. To master NumPy performance, remember this golden rule: profile first, optimize second. Never optimize without profiling, because you might waste time optimizing code that's already fast enough. Use the right profiling tools to identify bottlenecks and understand where your code is actually spending time. Make informed decisions about where to focus your optimization efforts based on real data, not guesses. With these profiling techniques and optimization strategies, you're now equipped to write faster, more efficient NumPy code. Happy profiling!
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.